So this is a short video lesson on Calc 4.2. So in the textbook section 4.2, and we're specifically going to be looking at how to calculate the area underneath a curve but above the x-axis. So the first thing we're going to do is we're going to look at finding the area under a curve of a function, and there's some specific parameters in terms of how far do I go left and right on my x-axis to find that area. So to do this, we're going to use our fundamental theorem of calculus, which is Theorem 4.9. This theorem states that if a function f is continuous on a closed interval, and again that was something that was very important for us in differential calculus, continuous on a closed interval a to b, and capital F is the antiderivative of f on the interval from a to b, then if I take the integral from a to b of f of x dx, that's going to be equal to the antiderivative of b minus the antiderivative at a. So let's go ahead and work on that for our function here above. F of x is equal to x squared. So the first thing that I'm going to do is I'm going to integrate this from my interval a to b, which in this case would be 0 to 2. F of x is x squared dx. So we're going to have to integrate this. So to raise the power by 1 gives me a 3, and I'm going to put 1/3 out in front to include that value. There's no real plus c here, mainly because we're doing a definite integral and we're talking about two values that we're starting at. Obviously I can see I have a x and y intercept at 0, 0. So then I'm going to go ahead and look at this function from 0 to 2. So 1/3 at b would be at 2, so 2 cubed minus the antiderivative of f of x at 0. When I plug in those values, I get 8/3 minus 0, so my final solution is 8/3. And 8/3, or around obviously 2.6 repeating, that's the area that can be found above the x-axis from 0 to 2, but underneath the curve x squared. Now let's make more sense of this and look at it in terms of a different function. Here we have f of x is equal to 4 minus the absolute value of x, and we have a graph of that below. So there's really two ways you can kind of approach this problem. The first way is obviously through the fundamental theorem of calculus. So we could look at integrating this function on the interval from -4 to 4. Now the problem with an absolute value function is that it takes on two different types of properties when it is positive or negative. When x's are negative, it's still positive, but it's going to be along this part of the function. Then when the x's are positive, I'm going to have values that are going to go on this part of the function. So let's take this integral and break it down at the middle, which is at 0, 0. And we're going to look from -4 to 0, and we're going to look from 0 to 4. So I'm going to rewrite this integral from -4 to 0, and that's going to take on the roles of when my x is negative. I have negative x's and I have positive x's. So here I'll have a minus a negative x dx, plus we're going to look at the integrand from 0 to 4, and this is where my x's are positive. So if I just rewrite this just to clean it up, because this is a minus and negative, so this would be plus -4 to 0 of 4 plus x dx, plus 0 to 4, 4 minus x dx. If I would integrate these two functions, I would get a 4x plus 1/2 x squared from -4 to 0. Plus, I'm going to look at the antiderivative of this part of the function, which would be 4x minus 1/2 x squared from 0 to 4. Either way, when I plug in, obviously, my zeros, here when I plug in 0, I'm going to get 0, minus when I plug in negative 4, I'm going to get negative 16, negative 16 plus a negative 8, so minus a negative 8 at negative 4, plus, here I'm going to have, obviously 4 is going to take me up to 16 minus 8, which is going to be a positive 8, minus 0, and minus the negative is going to be positive, so I get a value of 16 as my final answer. The area underneath this curve would be 16 squared units. Now, obviously, you can go about it that way, and you can kind of follow the math to get to that result. However, when you look at this problem in its graphical form, when you look at this shape that's formed by the absolute value function on the x-axis, it looks, and it is, an isosceles triangle. So don't be afraid to look at these problems in terms of functions that you can solve geometrically either. So I know my x-axis has a length of 8. I know my height is 4. So if I know how to find the area of a triangle, that would be 1/2 the base, which would be 8 times the height of 4. 8 times 2, or 8 times 4 is, obviously 32 divided by 2 is going to give me an area of 16. So you can see here that geometrically and also through calculus we can kind of get to the same result if we understand our functions and what their graphs look like. Okay, so let's look at a different problem, a little bit more challenging, not something that's so easily determined geographically, in terms of geometry. We want to find the area, so we're talking about intervals, the area of the region bounded by the function 2x squared minus 3x plus 2, bounded by the x-axis and the lines x equals 0 and x equals 2. So I obviously have some type of parabola-like function or a quadratic-like function over in the first quadrant because I'm bounding my x values from 0 to 2. So another way to kind of view this is we're looking on the region from 0 to 2 and given this function f of x. So the first thing that I want to do is I want to go ahead and, because this is a parabola, it might not be easy to look at it graphically, let's go ahead and just start integrating from 0 to 2. 2x squared minus 3x plus 2 dx. And when we integrate on this interval and solve for that value, we'll find the area in that bounded region. At any time during this process, if you ever feel confident enough with your steps, go ahead and pause the video and try the work on your own to see how you're comprehending. So the first thing to do is find the antiderivative of my function. So here, let's go ahead and raise my power to a 3. But because there's a 2 out in front, I want a 2 left over, but I need to divide by that 3, so that cancels. Minus x squared, but I want a 3 there, so I'm going to have a 3/2, plus 2x. And we're going to integrate this from 0 to 2. So now I'm going to go ahead and plug in those values. So in the first part, at 2, I'm going to have a 2/3, 2 raised to the 3rd power, minus 3/2, 2 to the 3rd power, I'm sorry, not 3rd power, 2nd power, plus 2 times 2. That's the antiderivative at 2, at the b value. And I'm going to subtract from that when I plug in 0 for x, 0, 0, 0, so this whole second part of this function is going to be equal to 0. So now it's just simplifying and solving for my value here. 2 to the 3rd power is 8. 8 times 2 is 16. I got 16/3. Minus 4 times 3, that's 12/2. And then here I have a positive 4. Right now I don't like denominators, and this is typically a problem that you would see on a non-calculator section. So I have to kind of get my like denominators here. I'm going to probably multiply everything by 3. So I got 16/3, or I'm sorry, multiply this by, get a like denominator of 3, 2, and 1, which would be 6. So let's go ahead and multiply 3 times 2 and 16 times 2. So that's 32/6 minus times 3 times 3, 36/6 plus 6 times 6, 24/6. So when I combine these, 32 minus 36, that's a negative 4/6 plus a 24/6, which is going to give me 26, and we can simplify that because there's a 2 that goes into both, so I have a 3 in the denominator and I have a 10/3 as my area. So that's just a quick synopsis on how to use the fundamental theorem of calculus to determine the area underneath a curve using antiderivatives. Now on this next page we're going to kind of talk about two special definite integrals. Obviously you guys understand the difference between a definite and indefinite. Indefinite is when I'm taking the integral with no bounds or no values here in my integram, whereas a definite integral is going to have values located on the integram and are going to bound my function. So here we're talking about two special definitions for definite integrals. If I'm given that f is defined at a value of x equals a, then if we can define that an integram from a to a of f of x dx is going to be equal to 0. If f is integratable, there we go, on a to b, then we can define that the integram from a to b of f of x dx is equal to b of a. We switched the defined endpoints, and what that ends up doing is it actually makes the entire integrand negative. It flips the value. So we're going to go ahead and use what we know about those two special definitions, and also use geometric formulas like the area of a triangle, right? Area of a triangle is equal to 1/2 base times height. Also the area of a trapezoid, right? So this is a triangle. Trapezoid. Area of a trapezoid is 1/2 height times base 1 plus base 2, where base 1 and base 2 are obviously parallel to each other. So we're going to look at these different integrands, and we're going to use our geometric formulas to kind of simplify and solve these types of functions. So here we have in letter A, we're asked to find the integrand from 0 to 1 of negative f of x dx. So because of that negative in there, we can always bring out a constant term, so we can rewrite this from 0 to 1 with a negative out front of f of x dx. And when I look at the function f of x here above, from 0 to 1, that's going to take me from here to here. So when I'm looking at this triangle, because it's below the x-axis, its area is going to be negative. Every area above the x-axis is positive, where areas below the x-axis are negative. So when I look at this right triangle, it has a height of 1 and a base of 1. Therefore, 1 times 1 times 1/2 would be 1 times 1/2 would be 1/2, and because there's a negative out in front, I would have a negative of a negative 1/2, so that would be equal to positive 1/2 area. Now we're going to look at from 3 to 4 here of 3f of x. Again, we can always take a constant out in front, so let's remove that out to the front of it. And when I'm looking at the function f of x from 3 to 4, 3 to 4 is going to take me from here, 3 to 4. So when I look at this function on this interval, it looks like I just have a rectangle. And how do I find the area of a rectangle? Well, that one's pretty easy. It's just going to be length times width. So my length looks like 1, my width looks like, or my height here looks like 2. So 1 times 2 is 2. But then remember, we had a 3 out in front, so when I multiply that by 3, I end up with 6. Here we're going to find the integrand from 0 to 7 of f of x. So nothing really going on in terms of in with the function. 0 to 7, however, is a larger interval. We're going from 0 all the way up here to 7. So we're looking at this function. Because we have multiple pieces here and we can kind of see the slopes of the lines, obviously this triangle, which has a base of 1 and height of 1, is kind of opposite of this base of 1 and this height of 1. Wouldn't you agree? So don't these two triangles, since they have the same area and one's above or below the x-axis, they're actually going to kind of cancel each other out. This area is negative and this area is positive, and when I add those together, they're going to add up to 0. The same would be true over here. This triangle is going to have the same area as this triangle. So once I get rid of that, what's left over is this funky little shape right here, which looks like it's kind of formed by 2 trapezoids, one trapezoid right there, one trapezoid right here, and the area that I found in that blue rectangle earlier in part B. So the area that we found in part B was an area of 2. So one piece of this integral or area is plus 2. The other piece is the 2 trapezoids formed on either side. The trapezoids have a base of 1 and a base of 2. So I'm going to add those bases together. I'm going to multiply it by the height. The height in this case is 1. And I'm going to also multiply it by 1/2. Now the only thing I also have to include here is that these 2 trapezoids are identical. So I'm going to multiply them by 2 because there's 2 of them, which kind of cancel the 1/2 and 2. 1 plus 2 is 3, times 1 is still 3, so 2 plus 3 is going to add up to 5. So here I have an area of 5. Let's look at part D now. From 11 to 5, from 11 to 5, let's look at that integrand, or that piece of the puzzle. So here we're going to start at 5, we're going to go all the way up to 11. So I'm going to highlight the part of the function that I'm worried about on this problem. Obviously we're kind of in that same boat of canceling triangles. This triangle right here in purple is going to cancel with this area of this triangle right here, since one's positive, one's negative. Same thing's going to happen here and here. What I'm left with is this integrand from 7 to 9, 7 to 9. So I can say that this one is kind of equal to the integrand from 7 to 9 of f of x dx. And it's kind of an odd shape, but let's kind of just split this right down the middle at 8 and look at it as in two different trapezoids, both with bases of 1 and 2, and they have a height of 1. So when I go ahead and integrate this, I'm going to have two trapezoids which are going to be equal to each other. So there's 2 of them. 1/2 the height, which is 1, times the basis, 1 plus 2. Again, the 1/2 and 2 kind of cancel the product, and all I'm left with is an area of 3. One thing I have to be really careful of here is the fact that the area that we're trying to find here between 7 and 9 is actually below the x-axis. So since it's below the x-axis, its value is going to be negative. Now let's look at part E and F. Again, at any time you can always kind of pause and try the problem on your own. This way you can kind of practice as we're going through the notes. So we're looking on integrand from 0 to 11, which is the entire function. And we can start looking at where I'm above and below the x-axis, because that helps me kind of narrow in on what parts of the function I need to add up. So here I'm above, but here I'm below, so let's go ahead and cancel those 2 right there. Again, here I'm below, and here I'm above, so let's cancel those right there. Here I'm above, yet here I'm below, so let's cancel those areas right there. What I'm left with are these two pieces right here. We can see that this trapezoid has a base of 2 and a base of 1 and a height of 1. And that trapezoid right there would also have the same area as this trapezoid, which had a height of 1, base of 2, base of 1. So they kind of cancel each other out. The same thing would be true here with this one. This one would cancel out with that one right there. So after all the canceling is kind of finished, all I'm left with, and whatever's not colored in, is this rectangle right here. So this integrand actually becomes quite easy to figure out because all we're worried about is this rectangle, which has a base of 1 and a height of 2. So 1 times 2 is 2, and the area of that function over that integral is 2. Let's look at f here from 4 to 10. From 4 to 10. So we're going to start here at 4, and we're going to go up to 10. So again, just looking at what we overlap or what is kind of coincides, this triangle with this triangle. And it looks like I have a trapezoid here, which is going to map with this trapezoid right here. So all that's left is a trapezoid and a triangle. So when I add up those two parts, right, I have the trapezoid, which is going to have an area of 1/2 the height times base 1 and base 2. Plus the area of the triangle, which is 1/2 base times height. So here I have a 3/2 plus a 1/2, which adds up to a total of 2. So, looking at our last question here in our notes, it's multiple parts, but let's look at the different types of functions and see how they would compare with each other. Here we're considering a function f that's continuous on an interval from -5 to 5, and we know about this function that its integrand, or the area under its curve from 0 to 5, is equal to 4. So when possible, we're going to kind of simplify and change our integrand so that it looks more like this, obviously, so we can use this fact. So right here, we're looking at an integrand from 0 to 5 of fx plus 2. Now, algebraically or graphically, when we took a function and added 2 to it, all we did was shift it up 2 spaces. And what that's going to do is, obviously, the area underneath the curve in the x-axis is going to increase. So we know that our area is going to be larger. So let's first take this sum, and let's break this integrand into 2 smaller integrands. 0 to 5 of f of x dx, plus, let's take the integrand from 0 to 5 of 2 dx. So 0 to 5 f of x dx, we know that's equal to 4 because that was given to me, plus, here if I want to take the integral from 0 to 2 of 2, that would then be equal to 2x by using my integration formulas. And if I'm looking at that from 0 to 2, that means I'm going to have 4 minus 0, so that's going to be 4. I'm sorry, 0 to 5. What was I thinking there? 0 to 5, 0 to 5. So 2 times 5, that's 10, minus 0, so what I'm going to have to do is add 4 to 10, and my overall area of this function is 14. Now what happens if the 2 is being added to the independent variable? So what that meant graphically was that my function would have been shifted left 2 spaces. Whenever we added something to the independent variable, that would shift my function to the left. Subtracting obviously shifts it to the right. So by shifting it to the left 2 spaces, what we can do to compare these two functions, because shifting left or right, moving a function left or right, does not change the area that exists underneath the curve. All it does is move the values. So what I can do with this integrand from 3 to -2 is, rather than moving it to the left 2, I'm going to move it back to the right by subtracting 2 from this independent variable, and therefore adding 2 to my integrand, or my integral. So I am shifted 2, but I'm going to move it back to the right 2 so it matches the given information that I have. So 3 plus 2 is 5, -2 plus 2 is 0, of f of x dx. So this function is going to have an area under the curve of equal to 4. So here in part C, we're looking at an integrand from -5 to 5 of f of x dx. They do tell me that this function f of x this time is an even function. And if you remember anything about even functions, they are symmetric over the y-axis, So because of symmetry over the y-axis, I know that the areas on either side of x equals 0 are going to be equal to each other. Okay, they're going to be equal to each other. So think about the function like y equals x squared. Because that specific function is an even function, the area on either side of the curve, as long as I go in equal distance on both sides of 0, so for example from -5 to 5, the areas are going to equal each other in total. So if I know that the function f of x from 0 to 5 has an integrand that's equal to 4, or has an integral that's equal to 4, then if I would also look from -5 to 0, and then from 0 to 5, both of these integrals would therefore be equal to each other because the function is even. So we can say then that this integral is equal to 4 plus this integral, which is equal to 4, and their sum then would be equal to 8. Now what happens if the function is odd? Well, again, when you talk about symmetry, even functions have symmetry over the y-axis, where odd functions have symmetry over the origin. And if you remember about that, if I plug in a -x, I end up with a, I kind of get flipped over the x and y-axis. So positive becomes negative and negative becomes positive. So with symmetry over the origin, that would mean that if I looked at a function, for example, like y equals x cubed, right, the area under the left-hand side from -5 to 0 of f of x dx plus from 0 to 5. If I look at the first part of this sum, the first part is going to be, since it's an odd function, is going to have a negative area because it's going to be below the x-axis. Whereas 0 to 5, and because of the symmetry, is going to have a, above the x-axis, is going to be positive. So here I know this is positive 4 because that's what was given to me. But because of the symmetric over the origin, the area on the other side of this curve would have to have the same area but of a negative value. So when I add -4 and 4, I get an area of 0. And that works in all cases when the function is odd. And I'm looking at an integrand that's equidistant from the origin. Okay? So again, I hope those notes are helpful, and they kind of lay out how we can find the area under a curve for different types of functions, as well as piecewise functions, and like we covered on the first page, dealing with any type of function using the fundamental theorem of calculus. So use these notes, rewatch if you need to. Hopefully that will help you in your first steps into integration of calculus. Thanks. Have a great day.